So in the last class, we applied the Schrodinger wave equation to the particle in a one-dimensional box, and we derived the expressions for energy of the particle and the wave function. Okay, I have written down these expressions again here. The energy En is equal to n square h square divided by 8 ma square, when n is an integer, and we observe that the lowest value of this n is equal to 1. Okay, so it can only take positive integral values. Okay, so even if I take the negative values, it does not make any difference because here n appears as n square. So whether I take positive or negative integer, they work out the same. Okay, so n is 1 2 3 not equal to 0. M represents the mass of the particle and A is the length of the box. Similarly, the wave function, the normalized wave function, okay, is given by square root of 2 by A, the length of the box, into sine n pi by A into x. And this n, okay, is called as a quantum number, okay, is called as quantum number. And the value of n specifies the state of the system. Okay, the value of n is equal to 1 or n is equal to 2 or n is equal to 3, it specifies the state of the system. In this case, the system is one particle in a one dimensional box. So n is equal to 1 represents one state of this system, and n is equal to 2 represents a different state. So n is equal to 1 and n is equal to 2 or n is equal to 3, they represent different states of the same system. Okay, now let us concentrate on this expression and try to list out some important points or important features that we observe. Okay, and whatever points we are listing down now, they are only applicable for the particle in a one dimensional box, the energy of the particle in a one dimensional box. But some of the points that we will note down here are very important because we can generalize them for this quantum mechanics. Okay, so let us observe some important points related to energy. So the salient features of energy En of the particle in a one dimensional box. Now, while deriving the expression for the energy, when applying the Schrodinger wave equation, remember we set the potential energy of the particle is equal to 0. Okay, at the very beginning of describing what do you mean by particle in a one dimensional box, we defined or we set the potential energy of the particle inside the box equal to 0. That was purely for our convenience. So if the potential energy of the particle is equal to 0, then the total energy is nothing but the kinetic energy of the particle. You know, the total energy is sum of kinetic energy and potential energy. Now since potential energy in this case is 0, the total energy is nothing but the kinetic energy of the particle. So the total energy expression that I have written here is also the kinetic energy of the particle because potential energy is 0. So the first important observation that we make here is the energy En is nothing but the kinetic energy of the particle. Okay, the energy En is nothing but the kinetic energy of the particle because the potential energy was set equal to 0. So this n square h square by 8 m square is not only the energy, it also is the kinetic energy of the particle. The second observation that we make here is, let us see on what different factors this energy depends. This energy depends on the value of n. So by substituting different values of n, keeping other things constant, I can vary the energy of the particle. Similarly, if I change the mass, that means if I replace the one particle by another particle having different mass, the energy changes. So energy depends on the mass of the particle. And thirdly, it depends on the length of the box. So if I decrease the length or if I increase the length, so if I vary the length of the box, the energy of the particle also varies. Okay, if A is very very large, then energy becomes very very small, or if A is very very small, then energy becomes very large. So the energy depends on N, M and A, but it does not depend on x, that is the position of the particle. So if you look at the RHS of this equation does not contain the term x, that is the position of the particle. So the energy of the particle remains constant for a given value of n, m and a. It does not depend on the position of the particle. So if I again redraw the particle in the one-dimensional box, so this is x is equal to 0 and x is equal to a. The particle of mass m, okay, a particle of mass m is located somewhere, okay, it is somewhere located at point x, and it is not a stationary particle. It will be in continuous motion because all its energy is in the form of kinetic energy, so it will be in continuous non-stop motion. So if I select a particular point x, or I will call it as x1, and calculate the energy of the particle, that is n square h square by 8 ms square, and I will select one more point somewhere here and call it as x2, and if I calculate the energy of the particle at this point x2, its energy will be same because the energy does not depend on the position of the particle. So for a given constant value of n, m and a, the energy of the particle will remain same throughout the length of the box. So that is the second important observation. Energy depends on n, m and length a. But if the particle is fixed, that is mass of the particle is fixed, the two key factors are n, the integer, and the length of the box. If the length of the box is also fixed, the one key factor that affects the energy of the particle is the value of n. So as the value of n changes, energy also changes, but it does not depend on position. For a given value or fixed value of n, m and a, energy remains the same, throughout the box. What does it mean? That is, En does not depend on x, the position of the box, provided the others are kept constant. This is a very important observation of the energy of the particle. The third and most important is, okay, let us look at this equation again. Okay, the energy of the particle is n square h square by 8 ms square, where n takes values 1, 2, 3 and so on. So the value of n is only integer values. N can be equal to 1, 2, 3. N cannot be equal to 1.5 or n cannot be equal to 2.25. So the value of n is restricted to take integral values. So if the value of n is restricted, it means that the energy values are also restricted. What is the meaning of this? Let us calculate. So what is the lowest value of n? The lowest value of n is equal to 1, and corresponding to n is equal to 1, we have energy E1, which is the lowest energy of the particle in the one-dimensional box. So the lowest energy E1 is obtained by substituting n is equal to 1, so it becomes h square divided by 8 ma square. What is the next allowed energy? That the next allowed energy is obtained by substituting n is equal to 2, because after n is equal to 1, the next possible value of n is 2. N cannot be equal to 1.5 or 1.6 or 1.75. The next value is n is equal to 2. So if I substitute n is equal to 2, this becomes 2 square, that is 4h square divided by 8 ma square. Okay, similarly, the next allowed energy will be E3 is equal to 9h square divided by 8ma square. Okay, this corresponds to n is equal to 1. This corresponds to n is equal to 2. This corresponds to n is equal to 3. Let me calculate one more energy. E4 is equal to 16h square divided by 8ma square for n is equal to 4. Similarly, n is equal to 5, 6, 7, you can calculate. So, n is equal to 1 represents the lowest state of the system. Similarly, n is equal to 2 represents the next higher energy state, which is an excited state. Similarly, n is equal to 3, 4, 5, etc. They also represent different states of the system, but they all represent the excited state. So the ground state of the system is represented by n is equal to 1, which has energy h square by 8ma square, which is the lowest possible energy the particle can have. Now what I will do is, I will arrange this energy in the increasing order. Okay, in the increasing order. So as I increase the value of n, the energy of the particle also increases. So let me arrange them in the increasing order. So this responds to n is equal to 1. The energy is E1 is equal to h square divided by 8ma square. This represents the state of the system having the lowest energy. So this represents the ground state of the system. Remember, I told you, what do you mean by state? The state of a system is specified by the value of the quantum number n. So n is equal to 1 represents the lowest state of the system having the lowest energy. So this level of energy is called as an energy level. The next state that the particle can have corresponds to n is equal to 2, which has energy E2 corresponding to 4h square divided by 8ma square. What is the next allowed energy level or the state? It corresponds to n is equal to 3, which, and it has energy E3, that is 9h square divided by 8ma square. Okay, somewhere here n is equal to 3, E3 is equal to 9h square divided by 8ma square. Similarly, I will draw one more level, okay, corresponding to n is equal to 4. The next possible level is n is equal to 4, having energy E4, which is 16h square divided by 8ma square. So by placing the energies in the increasing order, okay, these are the allowed energy levels the particle can have. So by looking at this, okay, you can come into some conclusion immediately. One thing is, if we ask the question whether the energy of the particle can be varied continuously or not, the answer to this question is definitely not. We cannot vary the energy of the particle in one-dimensional box continuously, or in other words, the energy of the particle is restricted, or it is quantized, or it is discrete. Remember, this energy quantization is not a big surprise to us, because the very fundamental of quantum theory is to say that the energy of the particle is always quantized. So here also we observe that the energy of the particle is quantized. It is restricted to take only few certain values. For example, the lowest energy is h square divided by 8ma square. What is the next possible energy? The next possible energy or the allowed energy corresponds to n is equal to 2, that is 4h square divided by 8ma square. So the particle cannot have any sort of energy between these two values E1 and E2. For example, after 1h square by 8ma square, the next possible energy is 4h square by 8ma square. So it cannot have 2h square by 8ma square, or 3h square by 8ma square, or 3.5h square divided by 8ma square. All those energies are forbidden. Similarly, after the 4h square by 8ma square level, the next possible energy the particle can have is 9h square divided by 8ma square, corresponding to n is equal to 3. So 7h square, 8h square, 9h square, all those energies are not allowed. The next possible energy is 16h square divided by 8ma square. Now this energy E1 is h square by 8ma square. So if I look here, this h square divided by 8ma square is nothing but E1. So E2 is nothing but 4 into E1. Similarly, here I have h square by 8m square. So E3 is nothing but 9 times E1. Similarly, here also I have the same term h square by 8m square, which corresponds to E1. So this is nothing but 16 times E1. So E2 is nothing but 4 times E1. This is 9 times E1. This is 16 times E1. Okay, so we are expressing all the energies of different levels in terms of the energy of the ground level. So this is 16 times E1. So the first observation that we have made from this diagram is that, okay, energy of the particle trapped in the one-dimensional box is quantized. It is quantized. So it can only take a few restricted values. It cannot take all the values. Another important observation that we can make from this diagram is the spacing between the energy levels. Okay, or I will call it as energy gap. So what do you mean by energy gap? It is the difference in the energy of two successive energy levels. So you can call it as either spacing of energy level, or you can also call it as energy gap. So let us see, okay, what happens to the spacing between the energy levels as the value of n increases. So as the value of n increases, what happens to the gap? So it is well demonstrated in this diagram. You can see that as the value of n increases, the gap between two successive energy level also increases. So let us calculate what is this energy gap. This energy gap delta E is E2 minus E1, which is, what is E2? 4E1 minus E1, that is 3 times E1. So the gap, energy gap between these two levels is 3E1. Similarly, if I calculate the energy gap, this energy gap delta E is now energy of the third level minus the energy of the second level. Energy of the third level is 9 times E1 minus 4 times E1, which is 5E1. So you can clearly see that this energy gap is greater than this. Similarly, if you calculate this energy delta E, energy gap is 16E1 minus E3, that is 9E1, which is 7E1. So the gap between the energy levels increases as the value of n increases. So the energy levels are not equally spaced. As the value of n increases, the energy gap also increases. So this is a very important observation. The energy levels are not equally spaced, as the value of n increases, as the value of n increases, the energy gap also increases. The energy gap also increases. Okay, let me make one more important observation. Okay, that what is the lowest energy the particle can have? According to our classical idea, that is classical physics, the lowest energy the particle has is 0. As you decrease the temperature of the particle or the system, the energy of the system or the particle decreases with the temperature, and when we reach the absolute zero temperature, what do you mean by absolute zero temperature? 0 Kelvin. So when we reach the absolute zero temperature, all the systems should have zero energy. So according to classical mechanics, the lowest energy or the ground state energy any particle should have is 0. That is the idea of classical theory. But let us see here whether we get 0 energy. Okay, so how do you represent the ground state? The ground state is represented by n is equal to 1. And what is the energy corresponding to n is equal to 1? That is the ground state. It is h square divided by 8 ma square, which is definitely not equal to 0. So the lowest energy the particle has in this particular case is not equal to 0. And this non-zero energy the particle has even at absolute zero temperature is called as 0 point energy. Okay, so in this case the particle possesses a minimum energy called as 0 point energy, and this 0 point energy is very important from your spectroscopic point of view. When you are studying vibrational spectroscopy, this 0 point energy becomes a very important point of discussion. So the fifth important characteristic of the particle in a one-dimensional box is the lowest energy of the particle. Okay, I'll erase this off. The fifth point, the lowest energy of the particle in this case, that is in the one-dimensional box, that is E1 is not 0. Okay, therefore a minimum non-zero energy exists even at absolute zero temperature. Okay, so a minimum non-zero energy exists even at absolute zero temperature. Okay, that is, what do you mean by absolute zero temperature? T is equal to 0 Kelvin. So a minimum non-zero energy exists even at absolute zero temperature. This minimum non-zero energy is called 0 point energy. Is called as 0 point energy. Therefore, what is the 0 point energy for the particle in a one-dimensional box? It is E1 is equal to h square divided by 8 m a square. So this is nothing but the 0 point energy for the particle trapped in the one-dimensional box. Particle trapped in the one-dimensional box. Okay, now I think these 5 points are sufficient at this level. Okay, at your undergraduate level of studying quantum chemistry, these 5 observations are sufficient. But for curiosity, I will add one more interesting feature of this energy, that is, under what conditions this quantum limit will become a classical limit. Okay, what do I mean? So at what condition this quantization of energy of the particle can be replaced by the idea of continuous energy, which is a classical point of view. So under what condition this quantization, that is a quantum mechanical condition, can be replaced by a classical condition, that is energy is continuous. So for that I will consider a simple example. Okay, I will erase these 5 points. Okay, so I will redraw the energy levels. So this is the ground state energy level E1 for n is equal to 1. Okay, this is E2 which is 4 times E1 for n is equal to 2. This is n is equal to 3, having energy 9E1, and similarly n is equal to 4, corresponding to energy 16 times E1. Okay, 16 times E1, and the spacing between them, here the energy gap is 3E1, here the gap is 5E1, here the spacing is 7 times E1, where E1 is h square divided by 8ma square, where m is a particle of m is the mass of the particle, and we are assuming the particle is of very small size, okay, because quantum mechanics is applicable to subatomic particles or atomic particles. They are not applicable to macroscopic particles. So this m represents the mass of a very tiny particle such as electron. So the value of m is 9.1 into 10 to the power minus 31 kg, which is the mass of the electron. So mass is here a very small number. Okay, so when we are speaking about atomic particles or subatomic particles, the length or the dimension these particles travel is within the atom or within the molecule. Okay, I already told you in the last class, particle in a one-dimensional box is applicable to a conjugated molecule such as 1,3-butadiene, and the length of one molecule of butadiene is order of few angstroms or nanometers. Okay, so these particles, that is electrons, are subjected to motion of very small length of the order of angstroms or nanometer. So the mass is of the order of 10 to the power minus 31 kg, that is nearly roughly the mass of the electron, and A is of the order of few nanometers or few angstrom, that is nanometer distance. We are not speaking about very large distance such as 1 meter or 1 centimeter or 1 millimeter. Those distance are applicable for macroscopic particles. We are speaking about the movement of microscopic particles. So A is the order of angstroms. So A is very small. Mass is also very small. So what happens to E1? E1 becomes a very significant number. So if E1 becomes significant, 3 into E1, 5 into E1, 7 into E1, they also are very significant values. What does it mean? It means that this E1, 5E1, 7E1s are very large values. So you can differentiate the one energy level from the energy level clearly, because the separation between these two energy levels is very large, because E1 is also very large. So you can clearly distinguish the separation of one energy level from the another energy level. It is nothing but the principle of quantization of energy. So you can distinguish one energy level from another energy level. So this is the quantum limit. Quantum limit, where the length of the box is roughly of nanometer or in the order of angstrom, that is the dimension of an atom, molecule, atom or a molecule. So this is the quantum limit in the microscopic world. Now what I will do is, it is a thought experiment, I cannot do in reality. So what I will do is, I will take that particle from a nanometer dimension and I keep the particle in a dimension corresponding to macroscopic particle, that is of the order of centimeter or meter. So this A becomes very large number. Okay, in such case, if when A becomes very large, it is in the denominator. So A becomes large, A square becomes further large. So what happens to E1? E1 automatically becomes a very small number, because I have increased the value of A nearly 10 to the power 10 times more. Okay, not 10 times more, 10 to the power 10 times. ಯಾಕಂದ್ರೆ ಇಲ್ಲಿ ಆಂಗ್ಸ್ಟ್ರಾಮ್ ಅಂದ್ರೆ 10 to the power minus 10 centimeter. ಸೊ ಅದನ್ನು 1 ಸೆಂಟಿಮೀಟರ್ ಬಾಕ್ಸಿಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಿದರೆ, ಒಂದು ಆಂಗ್ಸ್ಟ್ರಾಮ್ ಇದ್ದ ಬಾಕ್ಸ್ ಅನ್ನು 1 ಸೆಂಟಿಮೀಟರ್ ಬಾಕ್ಸ್ ಇಂದ ರಿಪ್ಲೇಸ್ ಮಾಡಿದರೆ, ಸೊ ನಾನು ಏನು ಮಾಡ್ತಿದ್ದೇನೆ, ಲೆಂತ್ ಆಫ್ ದಿ ಬಾಕ್ಸ್ ಅನ್ನು 10 to the power 10 ಟೈಮ್ಸ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ತಿದ್ದೇನೆ. ಓಕೆ, ಸೊ ಇಲ್ಲಿ ಎ ಸ್ಕ್ವೇರ್ ಇರೋದ್ರಿಂದ 10 to the power 12 ಮತ್ತೆ ಸ್ಕ್ವೇರ್ ತಗೊಂಡ್ರೆ 10 to the power 20 ಫ್ಯಾಕ್ಟರ್ ಚೇಂಜ್ ಮಾಡ್ತಿದ್ದೇನೆ. So what happens to the value of E1? The value of E1 significantly drops, because there is a large increase in the value of A. So in such case, E1 is very small. So the spacing 3E1, 5E1, 7E1 becomes very small. So in such case, what happens is, when A is very very large, you cannot distinguish or separate one energy level from another energy level. So E1, E2, E3, E4 are so much closely spaced. Why they are closely spaced? Because this spacing 3E1, 5E1, 7E1, those values are very very small, so you cannot separate or distinguish one energy level from another energy level. So in such case, this energy level appears as continuous. Okay, it appears as a continuous energy. So here you have an discrete energy levels, here you have a continuous energy, which is nothing but the classical picture. So classical picture. Okay, so from quantum limit of quantization of energy, we can come back to the classical concept of continuous energy if I increase the dimension of the box from angstrom to 1 centimeter. So if I place the electron in a box of length 1 centimeter or 1 meter, then the energy of the particle in such a box can be varied continuously. It means the quantization is now out of question. Now it is in the classical picture. Similarly, instead of changing the length of the box, if I change the particle itself, okay, if I replace a particle of very less mass, low mass, by a particle having very large mass, okay, the dimension is fixed. What I am only doing is I am replacing the particle with a heavier mass. So then also what happens, as this mass is in the denominator, so if you increase the mass, energy even increases, and again the spacing between the energy level decreases, and again we reach this classical limit. So the quantum limit, that is the concept of quantization of energy, it approaches the classical limit, that is having continuous energy depending on the mass and the dimension of the box. If both mass and dimension are very very small, of the order of roughly 10 to the power minus 31 kg, that is that of an electron, and if A is of the order of nanometer or angstrom, this quantization becomes very very important. This spacing is very very large. But if this M and A are of the order corresponding to macroscopic systems, if M is in grams or kilograms, or if A is of the order of 1 centimeter or meter, in such case the energy even becomes very very small, so the spacing between energy levels becomes insignificant, so we see a continuous energy condition, which is nothing but a classical approach. So this energy which is quantized may approach the classical limit if we vary the mass of the particle and the length of the particle. So under microscopic condition, quantization is important, but under macroscopic condition, this classical condition is sufficient. So this classical condition or classical mechanics is a special case of quantum mechanics. So quantum mechanics is applicable in both the cases, but we only apply it to microscopic particle. When it comes to macroscopic particle, what we have seen is the quantum mechanical approach or the quantum mechanical ideas slowly approach the idea of classical theory. So under ordinary condition, we can use classical theory instead of quantum theory, but under the strict microscopic condition, we have to use this quantum theory. So these are some of these characteristic features of the energy of the particle trapped in the one-dimensional box.